Hi there, this is hopefully kind of a short video on section 3.5, which is putting together what we talked about in section 3.1 about modeling exponential growth or decay, and then putting it together with what we've talked about in the previous sections and how we now have a more analytical approach to solving like exponential equations. And then we're also going to introduce another type of function called a logistic growth function or a logistic growth model. So you can read all of this. This is what we've talked about previously, how like if we're thinking about there being exponential growth or decay and you're presented with a growth rate, but you're also told that it's compounded or applied more often than the period that's referenced with that growth rate, then you can think about that growth rate actually being divided. Like, for example, if you're presented with an annual growth rate of 5%, but that it's compounded maybe monthly, that would mean that there's actually a smaller percentage, not 5%, but a smaller percentage that's applied each month. So, and that percentage would be 5% divided by 12. So you can come up with the different models, and remember the exponent position in the general model represents the number of periods that have occurred. And depending on the units that you want to use, you can come up with that model. So I have the two different ones here representing that annual growth rate of 5%, but compounded monthly, right? Where if you want t to be in years, then you would think, okay, after 1 year, 12 periods have occurred. So that's why we have 12t in the exponent position. But if we wanted t to be in months, well, that matches up with what the actual growth rate is, which would be 0.05 divided by 12. And if we think about the number of times per period that a percentage or a ratio is being added or subtracted in the case of decay, that's where we get the continuous growth or decay. And you can kind of read through the derivation for that. But with the base E, and kind of a cool thing is that and this is based on log properties, like you could prove this, but you can come up for exponential growth or decay, you can come up with the model that has base E, where then you could be thinking about there being continuous growth or continuous decay. So the example here that we had gone through, this one's pretty straightforward. Like you're given that the infection rate increases at an annual rate of 9% a year, compounding continuously. So just coming up with the model, like in 2003, we would treat that as t equals to 0. There were an estimated 25 million, so like A naught would be 25. And that's in millions of people who have been infected by HIV in sub-Saharan Africa. If the infection rate increases at an annual rate of 9%, a year, compounding continuously. So if we weren't given this part, then we could just come up with our model where it would be like the base would be 1 plus 0.09. But because we are given that that's the annual growth rate being compounded continuously, it means like there's a small percentage being applied constantly. Write a model that represents the number of people in millions who have been infected since 2003. So coming up with that, like we could use A of t would represent the number of people or the population of people with HIV in sub-Saharan Africa. We can treat 25 million. Oh, and this would be in millions. If you wanted to make A naught and write out 25 million, you can. I'm just going to have the output here, A of T, represent number of people with HIV in millions. And then we can use base E to represent that continuous growth. R is 0.09 based on there being continuous growth, and then times T, where T will be number of years since 2003. Okay, so that's one where we have to come up with the model with base E, because we're given that the information that we're given about the growth rate has to do with it being compounded continuously. This next situation, radium-226, has a half-life of 1,600 years. If the initial amount is 5 grams, write a model for the amount of radium as a function of time in years. So I'll use R of T will represent the amount of radium 226 in grams. The initial amount is 5 grams. And then going off of this information, we're thinking, well, R would be minus 0.5, right? Like given the half-life, that's the amount of time that it'll take the amount to decrease by 50%, the amount of radium-226 to decrease by 50%, sorry. So 1 minus 0.5, and then thinking about, well, what is a period? Since we're given the half-life is 1,600, we know after 1,600 years, that's whenever that initial amount would be cut in half, like decreased to 2.5 grams. So I want, for determining, like if I thought about 800 years passing, well, that would be half of a period, right? So we're taking the number of years that have passed and dividing by 1,600, where T is in years. So simplifying that, you can use the basis 0.5 or 1/2, right? Either way. But here's our model. Okay. And I referenced this previously. I think you guys can kind of wrap your brain around like the caffeine situation a little bit better that was on your quiz. So like you drink a cup of coffee, there's a certain amount of caffeine in your system, whether it's like, let's say 200 milligrams. And we know the half-life of caffeine is about 5 hours. So after 5 hours, it's not like all of a sudden at the 5-hour mark that initial amount gets cut in half. Like you drink the coffee, you have this amount of caffeine in your system, and then the amount starts to decrease as time is passing and you're not adding any more caffeine. So we can think of that as being continuous decay. But we would need to figure out what the rate would be based on there being continuous decay. And so we can come up with this equivalent model that has base E. We have the initial amount, right? Like we know that R of T would still be equal to 5 times E, but we don't know what R would be. So we need to think about a point that we know lies on the graph of the original model that we came up with based on half-life. And how about we know after 1,600 years, there would be 2.5 grams of radium-226 left. So thinking about plugging in that point, so replacing R of T with 2.5. And then now this is an equation that you guys know how to solve. So if we divide by 5, right, we would have 1/2 equals E to the 1,600 times R. I'm just going to switch those factors. And then rewriting in the equivalent log form, 1,600 R is equal to ln of 1/2. So R is equal to ln of 1/2 divided by 1,600. So that means that the equivalent model with base E would be 5 times E times ln, to the ln of 1/2 over 1,600 times T power, okay, where T is still number of years that have passed. And you'd see, I think I still have this on here. If we graph both of them, like that's our original with the information about half-life, and then this is the model we just came up with, you can see that their graphs overlap perfectly. They represent the same graph. And if you thought about applying, you could even pause and try and do this. If you thought about trying to apply some of those log properties that we had previously talked about, like you could think about unplugging, and then we'd have base ease. So, and simplifying that, you would be able to do that. Okay, so logistic growth model. So exponential growth is unlimited, right? Like if we think about the graph of an exponential function that's increasing, so representing growth, as the independent variable, so whether it's x or t, approaches infinity, right? The output values of an exponential function where there's growth being shown would be approaching positive infinity, like it continues on forever. However, when describing a population, there often exists an upper limit L, past which growth cannot occur. So this upper limit L is called the carrying capacity, which is the maximum population that can be sustained or supported at time t as time t increases. So a model that's often used in calculus to describe this type of growth is the logistic differential equation. And this is actually something that would show up in like the BC level of calculus, or in college, like that equivalent level. You would be exposed potentially next year if you do take a calculus class, but usually it's more like the BC level. But this is called a differential equation. And I think conceptually, like we're not doing anything with it, but I think conceptually you could understand dy over dt would represent the rate of change of population. And if you think about this as being a function where dy over dt is the output, notice that the rate of change of population is dependent on the size of the population y. Now, L here is the carrying capacity. It's the largest possible population or amount. So the rate of change of the population is dependent on the size of the population, which is interesting. Now, K and L are positive constants. L, again, is the carrying capacity. A population that satisfies this equation does not grow, that's a typo, without bound, but approaches the carrying capacity L as t increases. And since y represents the population, you can kind of think about this. Well, if as time is passing, and when the population starts to approach L, notice that 1 minus the population approaching L, so think about it as like L over L, that would be 0. So that would mean that the rate of change of the population would be 0, and that's because that population is approaching that carrying capacity. So the rate of change of the population, the rate at which the population is increasing, kind of tapers off. So in the logistic differential equation, if y is between 0 and the carrying capacity, then the population is increasing as time is passing. If y is greater, so if the population is greater than the carrying capacity, then the population ends up decreasing. And I give in class the example of, like, let's say that there's this island and like 2 bunnies are dropped onto this island that we believe has enough resources for 20 bunnies. Okay, so if these 2 bunnies are dropped on there, they're going to start reproducing, right? At first, they'll be exponentially, they'll be reproducing, so they'll be growing in numbers. But then as resources start to be depleted, their population will slow down, like the growth will slow down and the population will taper out and approach that 20 bunny carrying capacity. However, let's say that same island, 40 bunnies were dropped onto it. Well, there's not enough resources to sustain those 40 bunnies. So then the population is going to start to decrease. We're going to focus on the situation of the population increasing. Now, the graph of y of t we call a logistic curve. And whenever there's growth, we call that the logistic growth model, but there could be decay. In calculus, you'll learn how to find the general solution to this differential equation. We're not doing it here, but I'm telling you that general solution is this model, this equation. And this is something that I would provide you guys. And then you're going to be like inputting values and solving for values in situations that can be modeled with logistic growth. So y of t represents the population. Here, L is still the carrying capacity. Okay, y of t is the population. Okay, t is time. Okay, C and K, though, are just constants. C is actually something we call a constant of integration. And again, to be determined in calculus. But there's comparing like a exponential growth graph and then a logistic growth graph, right? L is the carrying capacity. So we can see that as t is approaching infinity, right, y of t would be approaching whatever L is, whatever that carrying capacity is. And we can also see with the logistic growth model that at first, like the growth is kind of slow. It's very similar. Like if we compare like exponential growth, like at first it feels like there's exponential growth happening. And then there gets to a certain point in time where then all of a sudden the growth starts to slow down and there's a change in what we call concavity in the graph, which is also a calculus concept, but I think that you guys can understand the different shape in the graph. And I think we've referenced this before. So notice that at first the graph is kind of concave up, looks like a cup, and then it switches to being concave down, looks like a frown. Now this point right here where the concavity changes, we call the point of inflection. And we're not doing anything really with this, but I'm just kind of planting the seed for your future classes. So let's look at this example. A state game commission releases 40 elk into the game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 400 elk. So this would be L, the carrying capacity. 4,000 elk is the carrying capacity. And we can treat 40 elk as the population whenever t is equal to 0. So like that's a point that would lie on the graph. And then after 5 years, the elk population is 104. So that's another point that would lie on the graph. So we're going to come up with the model for the elk population in terms of time, which means, coming back here, I'm going to paste the model for us to reference. We need to solve for what the constant, we know what the carrying capacity L is, but we need to solve for C and K, or we could solve for negative K. So we do know that L is 4,000. So thinking about plugging in 0 and 40, that initial population, notice that when we set up, so I'm replacing y of t with 40, we know L is 4,000 divided by 1 plus C times E to the negative K, well, T is 0, which is going to allow us, because E to the 0th power will be 1. So that's going to allow us to solve for C. Now this can be done with like 2 different populations, like 2 different data points, but it just makes it so much easier whenever you know what the initial population is. So now the denominator can be written as 1 plus C. And if we multiply by 1 plus C on each side, we would have 40 times 1 plus C equals to 4,000. Divide by 40, and we get 100. So C actually ends up being equal to 99. And we don't have an interpretation of that value. It's a constant. And then we'll think about, in order to solve for K or negative K, let's plug in 5, 104. So that other data point. So thinking about replacing y of t with 104. And then we know C is 99 now. So now we just are left with the one unknown. And we're replacing t with 5. So solving from here, and you can even pause here and try solving on your own. But if I were to multiply by 1 plus 99 times e to the negative k times 5 power on both sides and divide by 104, I'm trying to keep the time on this video down. 4,000 divided by 104 would be 500 over 13. Subtracting by 1 on each side, that is going to be 487 divided by 13. Dividing by 99, we get 487 divided by 1,287. And then now we can rewrite this as negative 5k equals to ln of that ratio. Oops. And I'm actually just going to divide by 5 since negative k is what's in the formula. I'm just going to divide by 5, so I get what negative k is, and I can just think about replacing negative k. So ln of this ratio divided by 5. So now I can think about writing, and I'm going to actually I'm going to call the function e of t for the elk population will be 4,000 over 1 plus 99 times e, and trying to write that, what negative k is equal to. And this is for t in years. So if we want to estimate the elk population after 15 years, we can think about plugging 15 into this model, like the exact value of that approximation would be 1 plus 99 times e to the ln of 487 over 1287 divided by 5 times 15. And if you put that into your calculator, you get approximately 628.583. You can decide if you want to round up or down, but that would end up being approximately, either 628 or 629 elks is what we would predict the population to be in 15 years. Now, for how long will it take the elk population to reach 2,000? So 2,000, remember, is half the carrying capacity. So setting E of t equal to 2,000 here. Here, I'm just going to copy and I'm just going to copy and paste this. Okay, so we're set to try and solve. Now notice if we multiply by the denominator on each side and then we divide by 2,000, we will end up with 1 plus 99 times e to the ln of 487 over 1,287 over 5 times t equals to 2. And if we subtract by 1 and then divide by 99, we would have e to the ln equals to 1 over 99. So then rewriting in log form, we would have ln of 487 over 1,287 divided by 5 times t equals to ln of 1 over 99. So that ratio, t equals 5 times ln of 1 over 99 divided by ln of 487 over 1,287, which ends up being approximately 23.642 years. So if you want to say approximately like 24 years, but approximately 23.642 years would be how long it would take for the population, for the elk population to reach 2,000. And I also just want to point out one last thing, that notice that this point of inflection looks like it kind of cuts the graph in half here. So that point of inflection ends up corresponding to t comma whatever half of L is. So we actually just found the point of inflection in the graph of the model that we came up with for this situation. But again, that's more of like a calculus concept. But for now, you should be able to solve this equation for a variable that's in the exponent position using what we know from the previous sections.